Hi guys, today I'll be talking about homolytic and heterolytic bond cleavages, plus an introduction to radical halogenation, and I'll be giving more examples including acid-base arrow pushing mechanisms as well. So the first one I'd like to talk about are homolytic species. So in homolytic bond cleavage, a covalent bond will break in the original species, and then each atom during the decomposition reaction will receive one electron. So the basic reaction looks like this, where we have molecule/species AB decomposing into A radical plus B radical. One important thing to note is that we will be using arrows for the arrow pushing mechanism, and essentially we have two different types of arrows, one for homolytic and one for heterolytic. So the one for homolytic will require something called fishhook arrows, and they represent the movement of one electron, one single electron. And they basically look like a regular arrow except for the second half. So fishhook arrows will look like this, and you can see them in many forms. And if we want to draw out the arrow pushing mechanism, we have to draw the original bond between A and B to show where the electrons are coming from. In arrows, you must always show where the electrons are coming from and where they are going. So in species AB, we know that there is a single/sigma bond between A and B, and within this bond there are two electrons. And in order to get the A radical and the B radical, we have to know that the A radical has one electron here, and then the B radical has one electron here. Of course, there are lone pairs around the atoms, but we don't indicate that because it's not really relevant to the mechanism itself. So if we know that there are two electrons here, and if we also know that the fishhook arrows move one electron, that means we would need two fishhook arrows, one going from the sigma bond to A and the other one going from the sigma bond to B. This represents that one electron from the sigma bond goes towards A, one from sigma bond towards B. And if we do this, I'll show it more clear. You would basically write it like this on your exam or practice. Next, I'd like to talk about radical halogenation as it relates to homolytic bond cleavage. So in your class, you will see a general example looking like this, and this is basically where an alkane, more specifically propane in this case, gets reacted with chlorine and ultraviolet light to form either one chloropropane or two chloropropane. And I won't get into the major products or the selectivity of different halogens, but I'll make that in another video if you guys would like me to. But essentially, this radical halogenation has three main steps. The first one being initiation, second one being propagation, and the third one being termination. And for example, I'm not really going to go into details of each step and what it does and what it provides, but instead I'll be showing the homolytic bond cleavages that are being broken within the propagation, initiation, and termination steps. So here we have our first step. It's called initiation. And in initiation, we always start out with the molecule or the halogen molecule that we are reacting with. So in our case, it'll be chlorine. And this will be the case for every single initiation step, depending on which halogen you use. In this case, we're using chlorine. We know that in a diatomic chlorine molecule, it's just going to be a single bond between a chlorine and a chlorine. And then upon the UV rays, which will break the bonds between chlorine and chlorine, we will form two chlorine radicals. And this is exactly similar to the first example I showed of the AB decomposing into A radical and B radical. We know that there are two electrons between the sigma bonds, and if we want to get from this to this, we will need to break up those bonds. So we will use two fishhook arrows, one going from the sigma bond to the chlorine, and then the same thing for the other one. And this is going to be initiation step, and there's always one initiation step which gets the process going. So first is propagation step number 1. Once again, I'm not going to go into the details of how it works or stuff like that, because that'll be saved for another video, but my goal is to just show where the fishhook arrows go and how it moves. If we know that there are two electrons here and one electron here, and if we know that our final product is going to be hydrochloric acid, or HCl, which has two electrons here, that means that fishhook arrow would have to meet in the middle, forming that sigma bond between H and Cl. We know that there is one electron remaining right here, so that will go in on itself on the propane, and that basically forms the propane radical right here. From that step, we have our propane radical, and then another chlorine molecule from our closed system will eventually interact with that propane radical. And in this case, we know that there is one electron here, and there are two electrons between the sigma bonds of the chlorines. And if we look at our final product, we have a chlorinated propane called 1-chloropropane, and we also have another chlorine radical that'll be used later on in the reaction, or not later on, but another P1 step. The same applies here where we have 2 electrons here and 1 electron here. So one of the electrons from the sigma bond will meet in the middle with the radical electron from the radical propane. This will form the chlorinated propane right here. And then since we have 1 electron remaining, that'll point towards the chlorine itself, forming that extra chlorine radical. And finally, the termination step. Since the radical halogenation is basically a cycle of chlorinations or substitutions, there has to be some sort of way to end it. This is 1 out of 3 different termination steps. I'm going to show this one because it's the most simple and it shows the fishhook arrows the best in my opinion. So we know that there are chlorine radicals floating around. This could either interact with a propane radical forming the substituted alkane, but it could also interact with another chlorine radical in the system. If we know that there is 1 electron here and another electron there, that means that they could form a bond between each other, indicated by the fishhook arrows right here. This will form the 2 electron sigma bond between the chlorine, and this is just one of the ways to stop the reaction. Once again, the reason I'm showing radical halogenation is to show how the fishhook arrows work. None of this is in detail, and there are so many other factors, including other halogens, other alkanes, factors like thermodynamic favorability, statistical favorability, etc. I'll be making another video in the near future about radical halogenation and going into each step, each detail, and every little nuance to it. Next are heterolytic bond cleavages. These are really similar to homolytic, but the difference is that in this case, a covalent bond breaks unevenly. This means that one atom takes electrons, both electrons from the bond. And this will form ions. One will be a cation and the other one will be an anion. So another big difference is the types of arrow we will be using. Like I mentioned earlier, the homolytic bond cleavage uses the fishhook arrows, which represents the movement of one single electron. In this case, for heterolytic, we will be using the regular full arrow that you guys are used to. This represents the movement of 2 electrons. So if we look at this reaction over here, we have our species AB turning into A cation and B anion. If we know that the B is negatively charged, this means that the electrons will go to that atom. So we will also know that there are 2 electrons between the sigma bond of A and B, and if we know that B is getting negatively charged, this means that we will have to point the arrow towards B itself. So both of the electrons from the sigma bond will go to the B, forming this B anion and this A cation. Next is an example of a heterolytic bond cleavage. This example is good because it's identical to the AB to A plus and B minus scenario, except we're using actual atoms. If we look over here, we see that the chlorine is negatively charged. This means that it received the electrons. So we'll point the arrow towards the chlorine coming from the sigma bond. The H right here is now positive, forming a proton. This is because originally there were 2 electrons shared between the H and the Cl, but if the Cl took both / just one from the H, this means that the hydrogen lost 1 electron, forming that proton. Also, we have to indicate that there is a negative charge on the chlorine. This is because originally the chlorine had 7 valence electrons, but now since it took 1 of the electrons, it gained another one. And the formal charge of this will now be 7 minus 8, which is equal to -1. Thank you guys so much for watching, and once again, this was a very brief introduction to homolytic and heterolytic, and for each case there will be much more advanced examples like the radical halogenation, and for heterolytic there will be other examples like other acid-base reactions, SN2 reactions, etc. If you guys want me to go more into detail for those other topics, please let me know in the comments down below. Thank you guys so much for watching, and see you guys next time.